In order for a character table to be mathematically valid, there are certain relationships that must be true that exist between the different irreducible representations and other properties of the character tables. And so specifically, there are four different relationships, or I'm calling them here rules, that always hold true for every character table. And so we'll list what those rules are in this video, and then also show how they're true for one character table. So the first rule is that the sum of the squares of the dimensionalities of the irreducible representations of a group is equal to the order of the group. The second is that for any irreducible representation, the sum of squares of each group, of each character, multiplied by the number of operations in that class is equal to the order of the group. The vectors of two different irreducible representations whose components are the characters multiplied by the number of operations in that class are orthogonal. And the last one is that the number of irreducible representations and the number of classes in a group are equal. So, that's a lot of jargon. Like a lot of things that are sort of mathy, it's best just to see examples. So let's do that. So let's look at the C3V character table, which we've been looking at. Rule one, it's much simpler just to see in practice, okay? So this one is the sum of the squares of the dimensions equals the order. Well, the dimensionalities. So the dimensionalities, remember, was this first column. So if you just square these first column numbers and add them up, 1 squared plus 1 squared plus 2 squared, okay, that equals 6. And that's going to equal the order of the point group. Remember, the order of the point group is the total number of symmetry operations. That's 1 plus 2 plus 3, 6. So those will always be equal. That's rule number one. Rule number two tells you that basically for each irreducible representation, you can back out the order of the point group in a different way. And the way to do that is you're going to take the different characters of the irreducible representations. So for A1, it is 1, 1, 1, right? And so here you have 1, 1, 1, 1. So you're going to square all those characters, 1 squared, 1 squared, 1 squared, of course that's 1. And then you're going to multiply those squares by the number of symmetry elements for that character. So this one, there was only one symmetry operation because there's an invisible 1 there, right? So that's what this one is from. For C3, you have a 2 coefficient, there's a 2. For mirror plane, you have a 3. So there's a 3. You do that math and you get 6, which again is the order of the point group number, total number of symmetry operations, 1 plus 2 plus 3. So this rule applies for each of the irreducible representations in the character table. So we just proved it for A1. Let's check it for A2. A2, well, now you have 1, 1, and negative 1. So if you square all those, well, a negative squared is the same as its corresponding positive square. So this ends up being the same thing, right? And again, we have 1, 2, and 3 there because of 1, 2, and 3 here. Now we can do it from E. This one's going to be a little bit different. We have 2, negative 1, and 0. And there, so we do 2 squared, negative 1 squared, and 0 squared. 0 squared goes away. We have 1, 2, and 3. 1, 2, and 3. Lo and behold, 1 times 2 squared, that's 4, plus 2 times negative 1 squared, that is 6. So that works. So that's rule number 2. Rule number 3 is one that's kind of easy to remember, just because we always said that all these vectors or irreducible representations have to be orthogonal to one another. Just like the x, y, z planes are orthogonal to one another. You're setting up a situation here where this is all leading to, where you can use these vectors in different combinations to describe the whole symmetry space of a molecule. Just like you can describe any point x, y, z as a linear combination, is the math term we'd use, a linear combination of the x, y, z basis vectors. So, you have x, y, and z, you can come up with a vector like that by adding up different values of those basis vectors together. So we're doing the same thing here. I'll keep emphasizing that analogy to Cartesian space throughout the course, because that's really the best way to think about this. Because you can't visualize symmetry space, right? So we're going to take the dot product. The dot product of two vectors that are orthogonal is 0. And so there's just a little factor you have to do here. The dot product, again, is, so if we do A1 and A2, that's just multiplying each of the values, the corresponding values in the irreducible representations, and then adding them together. But what the rule tells us is that we have to add in a factor multiplying for the number of symmetry elements. It kind of makes sense, right? Because here you have 3 symmetry elements. So it's like there's some weightedness to the reflection symmetry elements because there's 3 of them. It's like 50% of the space is sort of this sigma V space because 3 out of 6 of the symmetry operations are sigma V. So we have 1, 1, and 1. First, I guess, because we're multiplying, let's actually back up. Since we're multiplying by the symmetry element coefficients 1, 2, and 3, I have 1, 2, and 3 there. And then I just multiply in the irreducible representation. So I'm checking A1 and A2. So I have 1, 1, 1, 1, 1, and 1. And I have 1, 1, and negative 1, 1, 1, and negative 1. Those should always have to be equal to 0. Otherwise, something's wrong with your character table. Okay, you didn't copy it down wrong, or if you're deriving it, you did not derive it correctly. So all the permutations, the dot products, are going to be perpendicular. So A1 dotted by E. Again, 1, 2, and 3. Those are the first coefficients. They came from the symmetry elements, 1, 2, and 3. And then we have 1, 1, 1. That's A1, 1, and 1. And then E, irreducible representations, 2, negative 1, 0, 2, negative 1, 0, 2 plus negative 2, 0, and then plus 0, 0. So that checks. Those are orthogonal. Last combination is A2 dotted with E. And there's a commutative property here. So if you say A2 dot with E, that's the same thing as E dotted with A2, okay, because it's just multiplication and division. But so here again, we have 1, 2, and 3. Those came from the coefficients of the symmetry operations, 1, 2, and 3. And then we have the A2 vector, 1, 1, negative 1, 1, 1, negative 1. And we have the E vector, 2, negative 1, 0, 2, negative 1, 0. And that also equals 0. So for all those permutations, all the vectors are all orthogonal to one another. Rule 4 is the easiest. This is just telling you that the number of classes and the number of irreducible representations is always going to be equal, always going to be the same, okay? So in other words, you always have a square-shaped matrix. Number of rows is always going to be equal to the number of columns. So here we have 3 symmetry classes. We have 3 different irreducible representations. We're in 3-dimensional symmetry space because we have 3 different classes of symmetry operations. Those are different dimensions. All right, so those are the 4 different rules. What I'd like you to do is prove to yourself that the 4 rules are true for the C4V character table. So go find the C4V character table online and work through these 4 rules. Test the dot products for rule 3. Make sure it's a square-shaped matrix for rule 4, etc. And do rules 1 and 2. And so if you're having problems with this, this is a great thing that we can do together during class. Normally during a non-COVID remote class, we would be doing this in groups together, okay? But we kind of can't really do group work as much anymore. But I'm happy to help you with this during our class times, which is basically turned into pseudo office hour times.